Hi, thank you for joining me. This is the first of 3 videos on dynamic range in digital cameras. Now, I won't be going over the basics on what dynamic range is, because I think there's tons of videos on YouTube that you can find that are great for that. But instead we'll be focusing more on what characteristic in the camera's design or in the sensor design either limits or expands dynamic range. In other words, what during the capture of an image influences dynamic range, and why you end up with this camera with 14 stops of dynamic range, whereas another camera would have only 7. In this video we'll look at the first step in which the dynamic range is limited, and we'll see that it's related to something called full well capacity. Just a quick side note before we start. In the beginning of this series, we'll ignore the influence of noise, sensor noise, on dynamic range. So in other words, we'll be studying virtually perfect and noiseless sensors, because you'll see that even without mentioning noise, you can still learn a lot of interesting things about dynamic range. So I drew kind of a pipeline bottleneck way of seeing it. That 12 stuff is just an example. So we're gonna focus mainly on these two things: full well capacity and sensor bit depth, the two main things that limits dynamic range for any camera. Let's remind everybody that when you gain a stop of light, you double the amount of light. And in the sensor, you double the amount of photons that arrive on one specific pixel. And because it's proportional, you also double the amount of freed electrons. If you have two objects in a scene that are one stop apart, the brighter one will have freed double the amount of electrons as the first one. And pretty much the same thing applies when you remove a stop of light, so the amount of light is halved, okay, and so are the photons and the electrons. So I said full well capacity is the maximum number of electrons one pixel can hold before it clips, before the signal saturates. So for example here, full well capacity is 32. So what it means is a certain number of photons will free up 32 electrons, and if there's even more photons arriving, the number of free electrons will still be 32. 32 is not by any means a realistic number, it's just a simplified version of a pixel. So if, let's say you have a white object in your scene and you expose it so that it just barely saturates the sensor, this white object will have freed 32 electrons during that exposure time. Alright, now you have a second object that is one stop darker than the white object. This one will, for that same exposure time, free up 16 electrons. Then one stop darker, 8 electrons. One stop darker, 4 electrons. One important thing to consider here is that we are working in a discrete space, and photons and electrons are integer values. You can't have half an electron, nor you can a quarter of a photon. And that very fact leads to a limitation of dynamic range. One object that would be 5 stops darker than the first white object would only free up 1 electron. And one object that is 6 stops darker wouldn't free any electrons at all. And basically the same thing would apply for an element that is 7 stops away from clipping, or 8 stops away, or pretty much anything beyond that. It wouldn't be recorded at all. We can say by this step, the dynamic range of the sensor has ended. So in this case, where the full well capacity is 32 electrons, the maximum theoretical dynamic range is 5 stops. So here we have the example of a sensor in which the pixel maxes out at 20,000 freed electrons. So here is the full well capacity. And that's basically the response curve of the sensor before anything digital happens. We're looking at how many electrons are freed depending on the number of photons arriving. Just as a side note, the ratio of freed electrons per photon during an exposure is called quantum efficiency. So in this example, in the graph you're looking at right now, the quantum efficiency is 50%, but that's by no means a rule. And what it means is that you need 2 photons arriving on your pixel to free up 1 electron. Now let's say we're here. Let's say we remove 1 stop of light. Okay, so we arrive here. We have now halved the amount of photons arriving, and thus we have half the amount of freed electrons. Now, second stop, we divide by 2 a second time, so we arrive at 5,000. Third step, 2,500, and so on and so forth. So we can see that the first stop, the highest stop of light before clipping, is the one that has the most information. But we can also see that the scale we chose in the x-axis, incoming photons, because it's linear, it's not really well suited for visualizing dynamic range. So if we change the scale to stops of light, now the curve looks like this. So it's the same curve. These 2 curves are the same. The only thing that's changed is the scale. Here it was incoming photons, now it's stops of light. And if you want to have a scale with stops of light, you have to point out what is your 0. So in our case, I chose to place the 0 at saturation, at the full well capacity. Alright, now let's take a quick break and enjoy this picture of a beautiful sunny day and in the snow, because it'll be the only time in this video where you'll be looking at an actual image and not some abstract bullshit. By the way, just as a quick side note, I'll be talking about sensitivity in later videos, but this clipping point doesn't depend on gain or ISO settings or anything like this, just to be clear. It stays the same no matter what you put in your settings. So you can see that the closer you are to saturation, the more information each stop will have. The highest stop of light before saturation will, in our example, have 10,000 electrons to describe it. You have to see 1 electron variation as a potential shade of gray later on. So what exactly do I mean by potential shade of gray? It's that at the end of the day, what we really want to know is how a change of light intensity leads to a change in digital values, and that's what we'll be focusing on in the next video. But before that, you have a change in number of electrons. And if a change of light intensity is not recorded in this step as a change in the number of electrons, then there's no way it will be recorded as a change in digital values later on. So that's why I'm calling it a potential shade of gray. If an object has a contrast of 1 stop and is exposed 8 stops away from saturation, it will then have 78 electrons variation to describe it. And if an object has a contrast of 1 stop but is 15 stops away from saturation, it will have 0 potential shades of gray, so it won't be recorded at all. So as you can see this, because each new stop of light basically halves the amount of potential shades of gray, you can define the analog dynamic range by how many times you can divide the number of electrons by 2 before reaching number 1. And we have an operation for this, it's actually log base 2. Log base 2 of a number is equal to how many times you can divide that number by 2. So as a quick reminder, I call it analog dynamic range because it's a first limitation that occurs before anything digital happens in the sensor, in the capture of our image. Now, having said all this, full wide capacity is not a number that you will encounter often, so that video was pretty much useless, I'm sorry. Now, but seriously, what is or are the characteristics of the sensor that influence the most full wide capacity? Well, the main decider for full wide capacity is pixel size. Not sensor size, pixel size. So basically, the bigger the sensitive surface of a pixel, the bigger the full wide capacity will be. So there's sort of a rule of thumb to link pixel size and full wide capacity. So definitely take it with a grain of salt, but the rule of thumb is this. You should expect about 1,000 electrons per square micron on each pixel. So supposing that this rule of thumb is close to reality, here are some examples with cameras that you may know. So as you look at these various examples, let me stress once again that the analog dynamic range is not the dynamic range. It is a first wide limitation of dynamic range, but it's not the only one. So don't look at this slide thinking you should expect 16 stops out of the A7S II, for example, because it won't be the case. We've just seen the first of several limitations of dynamic range. Alright, so that's it for this video. If you have any question, if you're confused about anything, feel free to leave it in the comment, I'll try to answer it. In the next video, we'll take a look at the second step during the capture of our image in which dynamic range can be limited, which is the ADC, the analog to digital converter. Bye.